Okay. Hello again. And so now we're actually going to start um, Santosh's favorite topic, time-independent perturbation theory. Okay. It is important. Time-independent perturbation, any kind of perturbation theory is important. Time-independent is the simpler one, where the perturbation is time independent. So, for example, I mean, why is perturbation important? Because just about anything you can study. So actually, I think I should get start drawing things. All right, so I'm gonna share my screen, and I believe this would be desktop 3 here. Okay. Yeah, looks like um, this should be correct one. So, so we're going to do time independent perturbation theory. What page was it? So now this is 4. And this is, for example, for all of light atom interaction, or I mean, so many other things. You have the nucleus, you have the electron, maybe in a ground state, and then it gets excited to a next excited state. And you could imagine some kind of, a light wave. Now, if so, the light wave, how does it only perturbs that electron. And, then you talk about a minus D dot E interaction, or if it's the electric field of the uh, electromagnetic wave, it induces a dipole, and it's a minus d dot e interaction. Or if the magnetic part of the electromagnetic wave somehow has a stronger interaction, then you'd get a minus mu dot b. Okay, so the b of this guy has a e and a b in it. And so, those are the types of interactions that you have. So these are potential energies, right? You place a magnetic dipole in a magnetic field, and the dipole and magnetic field interact like that. Or if you have an electric dipole placed in an electric field, then you have this type of potential energy. And the atom, of course, can be an electric dipole or a magnetic dipole, right? The electric dipole, you have the electron going around. And so, it has the seeds there of being a dipole. You have a negative charge, a positive charge, and they're kind of going around, so it's like a dipole. And the magnetic dipole, obviously, because the electron in motion is like a tiny current loop. So there's a magnetic dipole there also, right? And so these are, and the electromagnetic field just comes in and perturbs the atom. And that is then what you see all around you, right? The different colors, the resonances, everything that you experience, all the experiments you do are the consequence of an electromagnetic field perturbing the atom. So perturbation theory is important. The original Hamiltonian, what we know is that the Hamiltonian acting on, let's say these are the eigenstates of the Hamiltonian, and so you get the eigenvalues, right? And so this seems reasonable. Let's call it equation 1. Um, so this Hamiltonian now, it may have in the unperturbed situation, right? It was just H naught. Okay, so this is the unperturbed Hamiltonian. But now, there is a small perturbation. So how do I put that in? I'm going to put in a perturbation and H prime, and it's time independent. So let's say this is time independent, like maybe a steady electromagnetic field that's not changing in time. So time independent. And to make sure it's small, I multiply this by epsilon. And this epsilon, it's just a number, but it's very small. Okay. So I have the Hamiltonian in there. Um, so now then I can ask the question that what's the eigenvalue for the nth state? Okay. And clearly this nth value, previously for the unperturbed situation, it was just, maybe En naught or something. But now it's going to change because of the presence of epsilon. And so it becomes a function of epsilon, right? Actually, you know what? Let me write this epsilon a bit differently so that it doesn't get confused with E for the energy. So I'm going to write this as this. Okay. All right. So it's going to be a function of epsilon. So this, what's it going to be? So I'm going to define this as, because it's a perturbation, so I can write this as some kind of expansion where principally it is still the unperturbed value, right? So imagine this orbit of the electron, and mostly even when the light field comes in, it keeps going in that same orbit, but maybe it just wiggles, right, back and forth like that. And so there's a slight wiggle. So principally, it is still, the eigenvalue for the unperturbed state. So this nth state, you know, corresponding to the unperturbed Hamiltonian. Okay, so the eigenstate of the unperturbed Hamiltonian. But now you have some first order correction like that. And then there may be a second order correction. Okay, and so on. So perturbation theory is approximate by definition. But because it is small, we can make very powerful approximations. Okay, then the next thing is, what about the eigenvector for the nth state? So the eigenvector, so now it's not just n. I mean, it's not just n naught, which would have been the unperturbed eigenstate. It's going to be some function of epsilon, just like we did for the eigenvalue. This is also going to depend on epsilon. And so what is this going to be? Well, there's the unperturbed eigenstate. Okay, so this is the nth eigenstate for H naught, the unperturbed Hamiltonian. And let's say that it the this forms. I mean, because it's easy to make this happen, so forms an orthonormal basis. These unperturbed eigenstates form form an orthonormal basis. Okay. Now, what's the first order correction? So here's your first order correction to the wave function. Here's your second order correction to the wave function. Okay. So now the next step is that, well, let's just substitute equations 2 and 4 in one. Okay, so now what's equation 1? Well, there it is up there. So H is H naught plus epsilon H prime. Okay, so there's that. Acting on E sub n. Now E sub n is given in 3 and n is given in 4. So E sub n is what? Uh, so from equation 3, like that, right? Um, Acting on, and then I write out the bottom, I mean equation 4, this, that, that, there we go. Okay, so I have, okay, now, uh, oh, so, okay, so this is, this part is this E sub n. The state n is given here. I forgot to act with this upon state n, so I should just, maybe I can write it here. This guy acting on, okay. So this guy acting on this state is equal to the energy, the right-hand side, times the same state again. Okay, so that's what I get, right? Now I can, if these equations are to be equal, then I can equate the different orders of epsilon separately. The different orders of epsilon separately. Okay, so let's just do that. So let's look at the 0th order term first. Do I have a meeting soon? Looks like, no, I don't. I don't think I do. Let me just check quickly. Um, well, you know what? I think it's fine. Okay, so let's keep going. So 10, 28, 24, 5. Okay, equate the different orders separately. So let's do the 0th order, right? So I have H, so 0th order, so this would be e to the 0 or 1. So I have H naught on the left-hand side. I have H naught acting on N naught, okay? And then on the right-hand side, I just have the first term, En naught. Okay, so this is just your unperturbed equation, eigenvalue equation. What about the first order? And here things become interesting. Okay, so on the left-hand side, I have H naught, and I'm looking for the first order epsilon, so H naught acting on N1, the first order correction. Um, Okay, so H naught acting on that. But I also have epsilon H prime acting on N naught. Okay, so that's from the left-hand side. And on the right-hand side, I have E N naught going with the epsilon, the first order, so N1, right? And um, then I have the epsilon En1 going with N naught. So epsilon E, the first order correction to the energy with, okay, so this is equation 6. Okay. So, so that's what I get. Now, what I'll do, um, it turns out that I need to know, um, uh, I will need to determine for my next calculations, I would need to determine the overlap um, of the first order correction to the wave function or the state with the overlap between the perturbed portion and the unperturbed state. And what does overlap mean? That is, um, the overlap could be written as that, the outer product. Did I say outer product? I meant inner product, the scalar product. Okay. And I'll need to know that. So I need to determine this overlap. And how am I going to do that? Well, I'll just take the inner product of equation 6. Equation 6 is given right there. Equation 6. So take this equation 6, take the inner product of 6 with, okay, because I see an N1 here, right? I see these guys. So if I take the inner product of this equation with this, I will, I expect to get the result that I'm trying to get. All right, so let's just do that. So equation 6, and let's take the inner product. So I have, okay, so that's the first term, and then the next term, it's the second term, and then the right-hand side, it's the first, and then the next is, now remember we had said that the unperturbed eigenstates, they form an orthonormal basis. Okay, these do. So what that means is that this guy is equal to 0 if m is not equal to n, and 1 if m is equal to n. Okay, so we'll have to look at these two cases separately. All right, so let's do the case where m is not equal to n. So what do we have? You'll notice that H naught acting on M naught, it can act on the, this is a adjoint, its adjoint is equal to itself. So you can write this as E M naught. You'll get just that, right? So let's just use that here. So I have this M naught, and then I'm left with N1. And by the way, this is the overlap we're after, right? Okay. And it appears here also. Okay, then the next term is um, this I don't know. I don't know the perturbation, what type of energy operator it is, so I can't, I don't know what effect it would have. I have to leave it as is. And on this side, you have E and naught. Okay, that's the overlap we're interested in, and this term gives you a zero. So this tells me that the overlap, so I can solve for, there's the overlap, that these are the same things. So I can just solve for that. Okay, I can bring those terms to one side. So let's just take um, bring this m term over to the right. Okay, and then solve for, so what would we get? We've got just this left over on the other side. If we take the m term and bring it over to the right side, so we got this left. And of course, these two terms just, the coefficients you can separate out. And so you can see that that would be, okay. And so now I know what the overlap is. Let's call this equation 7. Okay. Um, let's now deal with the case m equals n, because there's some information there. Let's not ignore that. Okay, so in that case, again, we again do, we're still taking the inner product of equation 6 with m, with now we're taking it with n naught, right? So in this case, the inner product with n naught, because n and m are the same. Okay. And so what do we have on the left hand side? So equation 6 is given right up there, right? Equation 6 is right there. So just like we did over here, same idea. So now you have n, sorry. So inner product with n naught, and the first term is that. The next term is there, so that's your left hand side. And now the right hand side, okay, that's the first, and then the next last term, and this of course is 1. Okay. So in this case now, again, H naught acting on N naught. So you know what this is going to be. This is just En not. Okay, so I have the first term becomes En naught, and this is the unperturbed wave function. This is the first order perturbed wave function, the state, right? And so that's your first term. The second term we can't do much with. We just gotta let it be. Okay. Then this guy here um, is equal to En naught. Oh, okay. Hey, we got the same term as that. Okay. And finally, the last term is, oh, so this is an interesting result. You see how this just cancels with that. Okay. And so I actually get my first order correction to the nth eigen energy. Okay. And it is just the expectation value of the perturbation in the original unperturbed basis. Okay, that's an interesting result. So this is an interesting result. We found the first order correction. So let me look back at, here, this is the expansion, right? Presumably we will already know what the unperturbed eigenvalues look like. And now we have the first order correction. Okay, and it is, what is it? It is just the expectation value of the perturbation, the perturbing part of the Hamiltonian uh, in the original unperturbed eigen basis. Okay, and we know what these unperturbed wave functions are, and so we just have to now you tell me what kind of perturbation it is. Is it an electric field, magnetic field, whatever? And then I can stick that interaction in there and find out its expectation value in the original unperturbed basis. So that's an interesting result. The next thing I would like to do, so that's the first order correction to the energy value. Okay. Now and in fact, actually, so what does the energy actually become? So let me actually give you, I can calculate the second order also, but let's just do the following. So let's just write out here a result here. So therefore, the energy, right? So from equation 3, here's the new energy now after the perturbation. And so that's going to be, I'm just writing equation 3. So you have En0, the unperturbed energy for the nth state, plus epsilon En1, which I just calculated. Okay. And without proof, I'm also giving you the second order one because it will be useful for homework. But it's calculated using the same ideas. All right. And so, not surprisingly, it's a squared. So you would get something like this. Okay. divided by, okay. So I should mention here that, and then it goes on. So this is to second order, all right? So uh, to second order in epsilon, okay? And so I should just say that this guy, we did not derive this. We derived the first part. So I've just stated the result from the book. Because it will be useful for homework. All right. So we got the eigenvalue, but what about the eigenstate? How does the perturbed? Okay, let's just do the first order correction to the eigenstate. All right. So so now, I mean, what about the? So we've found the perturbed eigenvalues eigenvalues for the n states, right? What about the eigenstates? So let's just do the first correction. So find um, the first order correction. Okay, and how? Like by using our favorite technique, by inserting the identity operator. Okay, and so we have a orthonormal basis to work with, this one. Okay, and so how? We're just going to say n1, this guy is equal to summation over m. And so very soon you'll see why we did some calculation on the previous page. We found an overlap. And so why did we do that? Well, here you'll get the answer. So, okay. So I just used the identity operator. Now, we just calculated this on the other uh, slide, the previous page, the overlap. See, that's why we did it. So you remember this? We just calculated this guy, the overlap of the perturbed state with the unperturbed one. That's what it is. M with n, m0 with n1. That's it, right? And we did it for the m not equal to n case, so this is first, let's write out the m not equal n case. And so I'm just writing out the result from here. There it is. There it is, equation 7. So you use equation 7 for the m not equal to n case, and then you can use the equation, we also did the m equals n case after that, so we can use that as well. All right, but anyway, use equation 7. So what do we have for the m not equal n? Well, equation 7 gives me the answer. So I'm just going to write that out here. So first I have this, and now the overlap. I'm just copying down equation 7. Oh, it's fallen off. Okay, so all that. And now also the m equals n case, right? So the m equals n case is, I'm just putting m equals n in here. So Okay. And this guy we don't really know because, it canceled out, remember? So let's call this A. Okay, it's undetermined. Because remember, it just canceled out. Remember, those terms just canceled out. So we couldn't really determine it. Okay, so let's just call it something. Okay, so therefore, to order epsilon, what we have is that n, right, the new number state after the perturbation is the original number state plus the first order correction. Okay. And if I want to write out what that is, so n is the unperturbed wave function plus, now n1 is written out there, right? So did I number it? I didn't number it. So this would be 9. Okay, so all this is given in equation 9. So I just need to substitute it in here. So what would I have? There's the epsilon, of course, because basically I'm writing out this guy. So n0 plus epsilon n1, right? Epsilon n1. So epsilon, and I have this term, which is just a times um, n0, okay, plus, and now the m not equal to n part, so epsilon, and then, summation m not equal to n. Okay, so it's just the same thing. All right. Okay. So there you go. Okay. Now, there's one last little bit of interesting manipulation that let's require this new um, n, the perturbed n, to be normalized, at least because the normalization gets affected when you put in the perturbed, add a perturbed part to it. The unperturbed was normalized, but now let's require this new state to be normalized, at least up to order epsilon. That's an interesting thing because if you require this to be normalized up to order epsilon, then what that means is that this little part, uh, this A, this guy. So you look at what A is, and it's looking at the overlap between the unperturbed nth state and the perturbed part. And so I'm saying that if I'm going to require it to be normalized, then the overlap between the perturbed and unperturbed part should be 0. Because if I do that, then you're not adding, because this will mess up your normalization. You've added some more n0 to the original n0. So the requirement that this is normalized up to order epsilon means that the A is 0. Okay. So if I so that then gets rid of this term because of the normalization. All right. And so in that case, n would work out to be um, the original and not. Um, because and not was already normalized and this was messing it up. So this little part that got added on must go to zero. And that's why this overlap has to be zero. Okay, so now the solution, which I can use to do homework and stuff, is just this epsilon, and then I have to write it a third time, I guess. M0. Okay, so there you go. So that's your perturbed wave function. Okay, and so for homework, you will find that this result and the result that we got for the eigenvalue, you know, this guy here, these are very useful results. Okay, so we will put a box around them and celebrate them. Okay, so I think this would conclude our first look at time-independent perturbation theory. Um, all right, let's stop the recording now. And